First of all, I would like to thank organizers Dr. Mohammed Kamran Jameel and Rifa University for inviting me here. This is okay. Now I hope you can hear me. I will try to explain as Dr. Kamran said that he already informed us that the talk should be of basic level and then go to the advanced level. So I will start from the very basic definitions and then I will go to the some advanced research topics. Okay. So the topic of my talk is embeddings of graphs with Gallai's property in two-dimensional lattices. Okay, I will discuss what is embeddings, what is Gallai's property, and what are different types of lattices. Okay. Thus, we will start with some basic definition of walk. So a walk in a graph is a sequence of vertices where vertices can be repeat itself. While okay, thank you. ये छोटी है थोड़ी सी बस ठीक है because I want to use board थोड़ा सा खोल दें ठीक है okay now I hope the students who is familiar with the graph theory and has taken a course or just taking their initial course on graph theory, they are familiar with the concept of walk and path. A path is a walk without repetition of vertices, and a cycle is a closed path where initial and final vertex is the same. So now we will discuss a graph is connective. So in throughout my talk, I will discuss only connected and simple graphs. Simple graph means there is no loop or multiple edges between any two vertices of the graph. So all the graphs, okay, thank you. Okay, it's okay. No, it's okay. Fine. So all the graphs in my talk are simple, okay, and connected. So now this is an example of a graph where you can see that A, B, C, E, D is a path because there is no vertex is repeated in this path, while the bottom A, E, C, B, E, D is not a path, that is a walk. Here vertex E is repeated twice. So if we close this path, then we will get a cycle. Okay. Now this is a concept of homomorphic graphs. Before going to homeomorphic graphs, I hope you are familiar with isomorphism. Okay. We say that two graphs are G and H isomorphic if we define a function from vertex sets of G to vertex sets of H. So like that U and V are if they belong to H set of G, then this map phi of U, sorry, not this one, this is UV. This is an edge of an edge in H. So in other words, we have a bijective map from the vertices of G to the vertices of H. So two graphs are said to be isomorphic if we define. Now, this is a concept of homeomorphic graphs. So two graphs G and H are said to be homomorphic if we insert vertices of degree 2 on the edges. For example, you can see that this is a graph. The graph on the left side A is a graph without white vertices. The vertices on that graph consists of black vertices. Now the graph on the right side is also on the consists of the black vertices, while the white vertices we introduce to make them homomorphic graphs. So these two graphs are homomorphic. Throughout my talk, this concept remain at the end of the topic. So be careful while you are understanding the concepts, what are the homomorphic graphs. So I will repeat again, two graphs are homomorphic if we insert vertices of degree 2 on the edges to make them isomorphic graphs. So now tilings, we have different type of tilings, regular tilings, semi-regular Archimedean tilings, and demi-regular tilings. So in my talk, I will discuss only regular and Archimedean tiling. So what is a tiling? Tiling in fact is a embedding, can say that is a sort of mapping of different shapes on a plane. such that the regular polygons are used. So we will not use irregular polygons. Sometimes we use same type of polygons. So we have only three types of lattices, or we can say tilings, that map the planes. That are square tilings, hexagonal tilings, and triangular tilings. So this is the tilings, three types of tilings. On the left, we have a triangular tiling. On the middle, we have hexagonal tilings, and on the right, we have square tilings. These are only three types of regular tilings. Now we have 8 different types of semi-regular, or we call them Archimedean tiling. I hope the white text is visible. Not visible, I will repeat. The Archimedean tiling, these are 8 different types of Archimedean tiling. So what is meant by the numbers written on that inside a tiling? Let me go back. Here, you can see that if we choose any vertex, around that vertex, we need to check the shapes of that tiling. So you can see that here, around this vertex, we have triangle, 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 triangle. So this tiling is called 3 raised power 6 tiling. Okay. So around this vertex, choose any vertex, we have 3 hexagons. So we call this tiling as 6 raised power 3. So these are the names. Similarly here, around this vertex, we have 4 tiling. Now you can see that this tiling, we have 3, 3, 3, 3, and 6. So this tiling is named as 3 raised power 4.6. These are the standard names of tilings. Yes. इसमें कहाँ ये red वाला? Okay. So here you can also see that around this vertex we have 3, 3, 4, 3, 4. So name of this tiling is 3 square 4, 3, 4. So either you go around the clockwise or anti-clockwise. It doesn't matter. Okay. Now, similarly here, you can see that this is a triangle, this is a 12-sided figure, this is also a 12-sided figure. So these are 8 semi-regular or Archimedean tilings or lattices which exist in literature. So far you have heard that there is recent a research paper where few mathematicians found a tilings which is cover all the plane without repeating shapes. So you can see that these tilings are regular tilings, or mean we can say that the shapes are repeating itself. But recently a very good research paper is published where they have shown that in fact we can tile the plane without repeating any sort of tiling. Okay. So next is a demi-regular. I will not discuss that demi-regular tilings because in that demi-regular tilings we have different shapes of polygons. That polygons may not be regular polygons. So we have in fact 3 types of tilings. Okay. Regular, semi-regular, and demi-regular tilings. Okay. Our next is embeddings. Okay. लाइट आ जाती है तो फिर मैं एक्सप्लेन करता हूँ. जी जी.
आपने सेमी रेगुलर के लिए एक टाइलिंग दिखाई.
हाँ.
तो ये कंप्लीट लिस्ट है कि
कंप्लीट लिस्ट है. सेमी रेगुलर टोटल जो है ना आर्चिमेडियन टेसलेशंस वो 11 हैं. उसमें से 8 सेमी रेगुलर है और 3 रेगुलर है. ये कंप्लीट लिस्ट है.
इसके अलावा
बहुत सारी टाइलिंग्स हैं, बहुत ज्यादा टाइलिंग्स हैं. ठीक है, मैंने आपको बताया ना अभी रिसेंटली देयर आर मेनी टाइलिंग्स, लेकिन मेजर जो टाइलिंग्स है वो ये है. इन 8 को कहते हैं आर्चिमेडियन टाइलिंग्स. असल में ये आर्चिमेडियन टाइलिंग्स, इनके अलावा भी और हैं, बहुत ज्यादा आपको मिल जाएंगे. जैसे आप लोग अगर आप ग्राफिक के स्टूडेंट्स हैं तो आपको पता होगा बहुत सारे हमारे स्ट्रक्चर्स हैं, केमिकल के स्ट्रक्चर्स हैं जिसमें हम डिफरेंट शेप्स यूज करते हैं. ठीक है, लेकिन आर्चिमेडियन टाइलिंग्स यही है आपके पास.
डॉक्टर ये बाउंडेड टाइलिंग्स है कि अनबाउंडेड?
अनबाउंडेड है. अनबाउंडेड इनफिनिट टाइलिंग्स है. थैंक यू. Okay. I hope everyone see now. Okay. Now, what is an embedding? Now, embedding of a graph on a surface is in fact a map that maps the vertices of the graph to the different points of that surface. Okay. I will repeat again. What is embedding? So, embedding in fact of a graph to a surface is in fact a mapping that map the vertices of the graph G into the points of that surface, and where the edges maps onto the arcs of that surface. And obviously arcs do not intersect with each other. they intersect only on the common vertex point. So now if we have a plane and G be any graph, we embed that graph on that plane. If the edges do not cross, we said that graph is a planar graph. Otherwise, we call that a non-planar graph. For example, these are three different embeddings of graph onto a plane. But on the left side, this is not a planar graph, a planar embedding, sorry. This is a planar graph, but this is not a planar embedding. This is a planar embedding, this is a planar embedding. So we have different type of embeddings of one graph on a surfaces. Okay. Now, this is a famous example of a Peterson graph, which is a non-planar graph. I hope the graph theorists know very much familiar about this graph. This is a non-planar graph which has 10 vertices. Okay. Now, this is the research question. Okay, I'm going to present this. Now, behind that, we have discussed what is homomorphic graph, what is tessellations or lattices, two-dimensional lattices, what are graph embeddings, or planar graph, non-planar graph. Now, this is a really important question. In some 1960s, Gallai is a famous mathematician. He raised a question, do we have a graph such that on that graph, every vertex is missed by some longest path? What is meant by that? For example, what? Okay. Before going to further, we have to understand what is this question. Okay. Now, we said that a graph G has a Gallai's property if its longest path or cycles have empty intersection. What is meant by that? So, for example, if I take this graph, now first I need to find the longest path. Okay, we have already studied what is path. Path is a walk without repetition of vertices. So if I go from here to here, you can see that this path covers all the vertices of a graph. So the question is that, do we have such graph such that we find a path which missed every vertex of that graph? Okay, so the positive answer of this question was given by Walter in 1969. This is the first graph of 25 vertices where every vertex is missed by some longest path. I will give you more detailed examples in my next slide. So just this is the first planar graph with 25 vertices. So the actually question was not that to find the graph. We can find so many graphs. The question was to find the minimal possible graph, smallest possible graph. Oh, everyone can think that, okay, this is not a big problem. We can find smallest possible graph. No, this is not an easy task to find a graph such that every vertex of that graph is missed by some longest path. So if you take, for example, we have here 25 vertices. We will get 25 different paths. So every path here missed every vertex. Okay, we will find a path which missed any vertex of this one. So now this best known example so far is found by Zanfrisco, Voss and Walter independently. This is a graph of 12 vertices. This is the smallest known example of a non-planar graph whose each vertex is missed by some longest path. I will give you all the illustrations or different of these figures, how we can find the longest path. Okay, here you can see that. This is a graph of 12 vertices. Okay, in this graph, the bold lines are the longest path, which consists of 10 vertices. You cannot find any other path which has more than 10 vertices in this graph. There are total 12 vertices. So we find a path which consists of 10 vertices. So vertex 1 and 10 is missed in this path. But what about other vertices? Can we find similar path that such that vertex 2 is missing, vertex 3 is missing, vertex 9, 8, 7, whatever vertex want to choose? Okay, you will always get a path that miss that vertex. For example, you can see that here. This is an example where you can see that vertex 1 or 10 is missing. Here vertex 2 is missing, 11 is also missing, but we just need to check one. Okay, For example, if someone say, what about vertex 3? Can you find a path where vertex 3 is missing? Okay, here is a path where vertex 3 is missing. So in every path, you can see that we have a longest path of 12 vertices. The longest path in this graph is of 12 vertices, not less, not more. Okay, the length of maximum path is 12, 10, and the order of this graph is 12. So in this graph, there are other 4 different paths where you can see that vertex 6, vertex 8, and vertex 9 is missing. So this is the still smallest non-graph where each vertex is missed by some longest path. So this is still an open problem. If you try to find a graph less than 12 vertices, you will be able to publish a research paper in a very good journal. So this is not an easy to find the graph smaller than these vertices, but still you can do that. Now, this is this here I have shown you a graph of Walther of 25 vertices. As I told you that the problem is not to find the graph. You can find so many graphs homomorphic to these graphs. As we have studied, we just have to insert number of vertices on the edges of degree 2. We will get so many larger graphs which satisfy the same properties. But the problem is to minimize these graphs. Optimal, we have to find the optimal, because in graph theory we need optimal solutions, optimal answers to our questions, not the general questions. So, okay, this is the graph found by Schmidt is the smallest non-graph of 17 vertices. Such that every vertex of this graph is missed by any some longest path. You can find any. For example, if you here you can see these are 6 different longest paths where every vertex is missed by. I did not numbering here on the vertices, but you can see that here if you want to miss vertex 9, but first remember you have to find a path, not the you need to find the missing vertex, just you need to construct a graph so the maximum path in that graph exists. So we have different paths, and different paths miss different vertices, and you can see that this is the path shown where the vertex 9 is missed. Okay. Similarly, this is a graph where these vertices are missed. This is a graph where these vertices are missed. So in this graph, if we take intersection of all the paths, because every path misses some vertex, we will get empty intersection. So these are the positive answers to the Gallai's question, that do we have graphs such that each vertex is missed by some longest path. So these are the positive answer. Now, later that 1972, Tudor San Francisco raised a similar type of question. Okay, now he make more complex that question. Instead of saying that path, he said, okay, what about cycles? What about planarity? What about non-planar? What about connectivity of the graphs? You can see that in these graphs, we have one connected graph. This is a one connected graph. One connected graph means if we remove just one vertex, the graph will be disconnected. Okay, you can see that if we remove this vertex 11, the graph will be disconnected. Vertex 3, the graphs will be disconnected. So again, in this graph, we have one connected graph. So Zanfrisco raises the question that do we have small? Okay, the main point is small, not the larger one. K-connected graph where any set of J vertices is missed by some longest path or cycle. Now we have a more strong condition than the previous one. The condition is cycle. Can we have a cycle? The condition is can we miss more than one vertices? Not single vertex, more than 2, 3, 4 vertices. Okay. And about the connectivity, can we have 2 connected, 3 connected, 4 connected graphs? Okay, so this is a general definition. Let pk or ckj, obviously pkj means k connected and avoiding j number of vertices. K connected planar graph, similarly we have non-planar graphs, okay, missed by some longest path or cycle, any set of j vertices. Okay, for example, in this graph, if we consider 2 vertices, okay, just 8 and 7, the length of the path in the previous case here, okay, is of 15 vertices, then it will be reduced. So this is not the case. So we have to consider the maximum path in that graph. Now, this is the smallest known graph which is single connected graph, one connected graph, okay, where any set of j vertices are missed, and the length of the cycle is 3. For example, let me show you. Whatever you want to choose, order of that graph, doesn't matter. Okay, if you say that, okay, I want to miss 3 vertices, what, whichever you want to choose, okay, 1, 2, 3. Now the length of maximum cycle is this one, 3. We can find a cycle which miss these 3 vertices. Okay, if someone say, okay, I want to miss 4 vertices, now we have to increase the order of this graph. Okay, I make another copy. So in this graph, you can see that the maximum length of a cycle is 3, and any cycle which miss all the vertices of this graph is also of length 3. So the problem is now we have to find, this is a one connected graph. By removing single vertex, the graph is disconnected. Now this is a smallest non-planar graph, okay, which means every vertex of this graph, and we have a cycle. Hypohamiltonian graph, if you know what is about hypohamiltonian means if you remove a vertex, you will get a cycle in that graph, spanning Hamiltonian cycle. So this is so far smallest non-3 connected graph whose every vertex is missed by some longer cycle. Now this is another graph, non-smallest. Now remember this, now we are talking here cycles, length of cycles, not path, because if you can see that this graph, and let me show you other slide. Okay, here you can see that the length of path in this graph cover all the vertices, okay, but we are considering here cycle. So instead of talking about path, we will consider only cycle. In this graph, you can see that these are the 15 vertices, and this is the smallest non-example of a planar 2 connected graph whose each vertex is missed by some longer cycle, not path. Okay, these are longer cycles which, okay, here are some vertices are missing. You can consider here is a vertex, here is a vertex, and here is a vertex. So here, so we have total 15 vertices, 5, 5, and 5 on each layer. Here you can see that. So here these graphs, we have different cycles where every cycle is missed by some vertex. So if we take the intersection of these 15 different cycles, we will get an empty intersection. Now, so far, this is an open problem. So far, no 2 connected graph which avoiding 3 or more vertices is exist. So this is an open problem if you want to work a 2 connected graph where 3 or more vertices are missed. So for planar graph, 2 vertices and 2 connected graph, this is a graph for 2 connected avoiding 3 or more vertices. This is still an open problem. Now, these are the smallest known examples so far. Okay. For planar graph, we have graph 1 connected avoiding 1 vertex. The order of that graph is 17. And similarly, 2 connected graph, okay, here equality means recently using few computer scientists, not mathematicians, with the help of obviously graph theorists, as Dr. Kamran Jamil already told you, graph theorists and many other field scientists are working together. So few mathematicians and graph theorists make a program and prove that this is the smallest possible planar graph. We cannot find smaller graph, a planar graph. One connected such that everywhere, obviously we have a non-planar graph where we have 12 vertices, but in a planar graph we have 17 vertices. So this is a proof. But for the case of 2 connected graph where 1 vertex is missed, the order of that graph is 32. But this is not optimal graph. You can find that if you want to work on this problem. Now, 3 connected graph, and you can see that if we increase the connectivity, the order of the graph is increasing rapidly. So here 3 connected graph, adding 1 vertex, we have a graph found by Winner and Arya consists of 164 vertices. Less than equal to again means you can find smaller possible graph than this. Again, 1 connected graph, avoiding 2 different vertices. This is work done by Zanfrisco. This has 308 vertices. and two connected graph avoiding any two vertices. This graph is graph of order is 914. Now, three connected graph avoiding two vertices, we have a graph of order 14,694 vertices. So if you are able to construct a graph which is three connected, avoiding any two arbitrary vertices, then you will have a very good paper in this field. Now, here is this one was the conjecture, as I have already told you that we have one connected graph avoiding any set J of vertices. Thomson said that we can find maybe less than that. He conjectured that, but Zamfrisco proved no, we cannot find smaller graph than that. So we have, if we have to remove just one vertex in that cycle and find the maximum length of that cycle, so the graph will be of order 3j plus 1. Now, later on in 2001, Zamfrisco raised a question, do we have graphs which possess the same property? I mean, now we have a we have a graph in lattices, in infinite lattices, such that every vertex of that graph is missed by some longest cycle or some longest path. Okay, as I already told you that the problem is not to find the graph, but the problem is to find the optimal graph. So the first answer of this problem was given by me and my co-authors. This is a graph. Okay, this graph is consists of 20 vertices. Okay, in here you can see that these u, z, x are the number of vertices on each path. It can be 1, can be 2, can be 3. Okay, so now these are okay. These are all the possible longest path in this graph. The possible longest path in this graph is consist of 16 vertices which miss some vertex, and then we can again find a longest path which miss again another vertex, and so on. We can find 20 such paths such that each path is missed by some longest vertex. So if we take the intersection, we will get the empty intersection. 5 minutes. Okay, sorry. So this is the lemma which help us to embed these graphs. Now we come to the embedding. So as I have mentioned that Zamfrisco asked, do we have graphs in infinite lattices which possess the Gallai's property? In fact, finding a graph in infinite lattices is not an easy. So we take the already existing graphs and embed those graphs in two-dimensional different lattices. So we have, this is the embedding, okay, of this graph in square lattices. Okay, here this graph consists of 46 vertices. So this is still an open problem. We conjecture that this is the smallest possible graph, which is embeddable in square lattice. It consists of 46 vertices. If you want to work, you can find a smaller possible graph than which is embeddable in square lattice. Okay, this is another example of a graph which consists of 94 vertices. As you can see that if we change the lattice here, in this square lattice, the order of that graph is 46. Now, if we go to the hexagonal lattice, the order of the graph is increased. Now, if we go to now, these are the regular. Now, I will go to the semi-regulars. Now, this is the order of graph which is embeddable in 3, 4, dot 6, 3 cube, dot 4 square, 3 square, 4, 3, 4. What is meant by 3? As I have already mentioned you, it means that we have triangles, round a vertex, and a hexagon. Okay, so this is an embedding of that graph which consists of 32 vertices in 3, 4, 6. This is an embedding of a graph which is of 36 vertices, 3 cube, 4 square, and this is also an embedding. Okay, now I will skip all other embeddings, and now I will go to here. This is another graph which is a two connected graph which where every vertex is missed by some longer cycle. So now we will embed these graphs in lattices. You can see that the order of this graph is increased. Okay, here we have 144. Now 98. These are all the embeddings of these graphs. So this is the conclusion. Okay, you can see that if we talking about tessellation in tessellation square lattices where all the polygons are triangles, or we can say the triangular lattices, the order of P11 graph is 30, while the order of P21 graph is 92, and hexagon we have 94, and square lattice we have 46. These are the so far known optimal graphs. Okay. If someone wants to work on this field, he needs to find the optimal graph on square lattices. Okay. So these are some references. They are not visible here. Okay. If I have shared with you, I'm just okay. Thank you. Now,
thank you very much, Dr. Faisal. We are talking about embedding of graph on different two-dimensional lattices. First question. So what? When you define definition of path, we said that definition of vertex that we cannot be vertex. But when you define cycle, we said that closed path cycle. The question is that if the initial and vertex have initial and end vertex is created, then how we can say that is not a path, that is a cycle. Yeah, it is cycle. And when we define a definition of cycle, we can say that the closest path.
if we start from one vertex and cover all the vertices, so in fact, in the definition of the cycle, we have this flexibility, then we can repeat and we can find the cycle. That is
Why we can say that it is a closed path when we the word path.
that is not a path, that is closed path. So as closed path is a cycle. These are two different terminologies. If we say closed path, then that will not be a path, that will become a cycle. But that will not remain a path. We change the definition of it. Okay?
That's another question. Is there any physical significance of
Physical signals, there are so many. Seeing that we have so many in the computer networking. The different types of computers are placed on networks in the as a community. There are so many papers where the capacity of these words are discussed in computer science and other fields. Okay? And in fact, we have so many structures. Chemical it consists of similar sort of these types of items. Like nanotube. Nanotube, what is nanotube? Nanotube is the example.
the question from person?
Yes. I have a question. That you are great at everything when we are wondering about it. What is different between a lattice and a tile?
We have different types of filings. Okay. Lattices and tilings are not the same. Lattice require to cover a plane. If you can use different type of tiling. For example, you can take triangular tile, hexagon tile. Similarly, there is the same similar sort of things. There are no. Sorry.
You know, there two dimensions.
Yes.
So, lattice is a two-dimensional or maybe three or four.
Actually, we have worked on three-dimensional lattices as well and four-dimensional lattices as well. So, due to the shortage of time and Dr. Kamran was presentation should be 30 minutes. So, therefore, I'm unable to show you three-dimensional lattices. In fact, there are three-dimensional lattices, and in fact, even four-dimensional lattices. We have these type of graphs. We also embed on 3 and 4 high-dimensional lattices. So, for three-dimensional lattices, you can see that you have cubes, one cube and another cube and hexagon like polygonic different shapes. There are high-dimensional lattices. That's all.
और कोई क्वेश्चन है? यहाँ पे मैं थोड़ा कमेंट ये करूंगा कि मैथमेटिक्स जैसे बताया कि यूनिवर्सल लैंग्वेज है, इसकी अंडरस्टैंडिंग जरूरी है. तो कहीं अगर आपको इंग्लिश में इशू है, समझने में इशू है, तो आप इससे ना घबराएं. आप कह सकते हैं कि हमें मैथमेटिक्स समझ आना चाहिए, हमें इंग्लिश से लेना देना ज्यादा नहीं है. अगर हो जाए तो अच्छी बात है, ठीक है. हम उर्दू में अपने फीलिंग को, अपनी मैथमेटिक्स को ज्यादा अच्छे तरीके से एक्सप्रेस कर सकते हैं. तो अगर कोई ऑडियंस में से उर्दू में क्वेश्चन पूछना चाहे, बल्कि मैं
अपने फर्दर स्पीकर को भी ये कहूंगा कि वो उर्दू को थोड़ा सा इन्वॉल्व कर लें तो हमारी आसानी बतेगी समझने के लिए, क्योंकि मैथमेटिक्स को समझना चाहिए बजाय इसके कि मतलब हम फोर्सेज हैं ठीक है, मेरी बहुत अच्छी नहीं है तो इसलिए मैं भी चाहता हूँ कि जरा अंडरस्टैंडिंग होनी चाहिए मैथमेटिक्स की। आजकल चैट जीपीटी आ गया, बस सेंटेंस देखिए वो हमें इंग्लिश में आंसर मिल जाएगी, मैथमेटिक्स में आंसर नहीं मिलेगा, ठीक है, वो हमने खुद सोच लिया। अच्छा मेरा एक क्वेश्चन है, आप जो फैमिली डिस्कस हुई है कि हमने पाथ ढूंढना है, हमने साइकिल ढूंढना है,
लॉन्गेस्ट पाथ और लॉन्गेस्ट साइकिल।
इसी तरह अगर हम कोई और फैमिली इंट्रोड्यूस कराएं, फर्स्ट तो हम कहते हैं कि हमने मैक्सिमम बाइफर्टाइड ढूंढना है या हमने मैक्सिमम कंप्लीट ग्राफ ढूंढना है, तो क्या इस पर किया जा सकता है?
ढूंढा जा सकता है। आप ये एक खास प्रॉब्लम थी, ठीक है, ये कहाँ से प्रॉब्लम निकली? इनफैक्ट ये प्रॉब्लम निकली थी हैमिल्टोनिसिटी। हैमिल्टोनिसिटी क्या होती है कि आपके पास एक लॉन्गेस्ट पाथ हो या एक स्पेनिंग साइकिल हो आपके पास ग्राफ के अंदर, ठीक है। तो फिर जो पीटरसन ग्राफ है, तो क्वेश्चन यही रेज हुआ था, ठीक है, उधर से कि क्या ऐसा पॉसिबल है कि हम कोई ऐसा ग्राफ कंस्ट्रक्ट कर लें जिसमें हर वर्टेक्स कोई ना कोई एक लॉन्गेस्ट पाथ उसमें एग्जिस्ट करे, और जो वो लॉन्गेस्ट पाथ एग्जिस्ट करे, ठीक है, इस तरह हमें हर वर्टेक्स के कॉरेस्पॉन्डिंग एक लॉन्गेस्ट पाथ में, फॉर एग्जांपल मैंने जैसे अभी आपको बताया कि 12 वर्टिसेस का ग्राफ था, उसमें अगर आप कोई भी वर्टेक्स कंसीडर ना करें, अगर आपको कहा जाए कि इस ग्राफ के अंदर लॉन्गेस्ट पाथ फाइंड करें कोई भी, तो जब आप लॉन्गेस्ट पाथ फाइंड करेंगे ना तो आपको 10 वर्टिसेस का मिलेगा। आपने कहा ठीक है। तो इसी तरह अगर आप बाइफर्टाइड की बात करें, बाइफर्टाइड में तो ऑलरेडी एग्जिस्ट करती हैं। हाँ, डिफरेंट चीजें आप इन्वॉल्व कर सकते हैं, उसके ऊपर कंडीशंस लगा सकते हैं कि ये कंडीशंस हो, ठीक है। जैसे आगे फ्रिस्को ने कंडीशंस क्या इम्पोज कर दी इसी क्वेश्चन के ऊपर, उन्होंने कहा ठीक है एक वर्टेक्स नहीं, अब 2 वर्टेक्स मिस हो, 3 हो, ये इजी नहीं है प्रॉब्लम फाइंड करना, 2 और 3 तक तो है, लेकिन आगे 2 कनेक्टेड और 3 वर्सेस अभी स्टिल ओपन
इन
है।
शॉर्ट हम कोई और फैमिली लेके उसकी एम्बेडिंग या उसकी जो हम ढूंढ सकते हैं।
ऑब्वियसली आप अब लेटेसिस में असल में मैंके ने ना 2001 में ये कहा था कि इसने कहा कि स्केल लेटेस के अंदर ना ये पॉसिबल ही नहीं, स्केल लेटेस के अंदर आप लोग ऐसी फैमिली ढूंढ ही नहीं सकते। तो इवन ये पेपर बड़ी अच्छे जर्नल में, डिस्क्रीट मैथमेटिक्स में बहुत अच्छा जर्नल है, उसमें पब्लिश था। उसके इस पेपर को कंट्राडिक्ट करने के लिए हम लोगों ने ये काम किया था, हमने कहा था नहीं, हम लोग स्केल लेटेस हो गया, हेक्सागोनल हो गया या कोई भी लेटेस हो, उसके अंदर हम लोग एक ग्राफ ऐसा जरूर फाइंड कर सकते हैं जिसमें कोई भी, अब यहाँ पर एक चीज ठीक है, जो अभी जैसे आपने बात की है, हमारे पास जो स्केल लेटिस है वो बाइपार्टाइट, ठीक है, वो बाइपार्टाइट होती है, और हमारे पास बहुत सारे ग्राफ्स ऐसे थे जो बाइपार्टाइट नहीं थे। तो उन ग्राफ्स को इम्बेड करने के लिए हम लोगों ने पहले तो उनको बाइपार्टाइट बनाया। असल में जो क्वेश्चन है फाइंड कर सकते हैं डिफरेंट प्रॉपर्टीज के साथ एम्बेडिंग। इनफैक्ट एक है मशीन लर्निंग के अंदर बहुत अच्छा सब्जेक्ट है, ठीक है, जिसको बोलते हैं एम्बेडिंग, ठीक है। वो आइगन मैप्स होते हैं जिसमें आप हायर डायमेंशनल जो ऑब्जेक्ट्स होते हैं ना वेक्टर स्पेस में हायर डायमेंशन या आरएन के अंदर, उनको आप लो डायमेंशनल सरफेस के ऊपर इम्बेड करते हैं, डिफरेंट उसमें डिफरेंट प्रॉपर्टीज होती हैं।
थैंक यू।